This video is going to go over the idea of valence shell electron pair repulsion theory. So this is represented by an acronym which we call Vsepr, right? So valence shell electron pair repulsion theory is what we also call Vsepr, right? And so this idea of Vsepr theory, the words mean something, and so that's what we're going to talk about today. So Vsepr allows us to describe, anticipate, understand the shapes of molecules. And so, for example, shown on here are two models. The left is a model of a water molecule. Water is called bent, and the reason it's called bent is because it is not linear. It is a bent molecule, where it is not symmetrical. Carbon dioxide, however, is linear. And this has a pretty dramatic effect on the overall properties of these molecules. Water is a liquid at room temperature, but carbon dioxide is a gas at room temperature. There are a lot of other sort of aspects, properties of these molecules that are sort of determined by their structure. Because water is bent, we will talk about this in the future, but it is a polar molecule, but carbon dioxide is nonpolar, and that has a pretty dramatic effect on how it behaves. So their shapes have a dramatic effect on their physical and chemical properties, and that's why we care about the shape. So shapes of molecules, these are all models. These are more models. And here's an amino acid is shown with a ball and stick model. This is a picture of a three-dimensional model. This is alanine. And then of course DNA, this is a model of DNA. And so all the shapes that you're going to learn about, even the simpler shapes, we can apply those to more complicated molecules, because even if you know, you're looking at a molecule that has hundreds or thousands of atoms, you can always focus on one of those atoms and look at the shape of the atoms around it. The shapes or geometries that we're going to talk about, the molecular geometries, they all have names associated with them. So for example, this one's called bent. I think it's probably obvious why it's called bent. This one's linear. That one's probably pretty obvious as well. This is called trigonal planar. Trigonal means it's triangular shaped, which I think you can see. Planar means that it's flat, which I think you can also see. We'll have some three-dimensional models in class as well, so you can kind of get a good idea of three-dimensionally what they look like if these pictures aren't good at helping you visualize. This last one here is called tetrahedral, and we'll talk more about why that one looks like that and why it's called tetrahedral. It actually sort of forms, if you connect all the outer atoms to each other, it forms a four-sided figure, which in geometry you would learn is called a tetrahedron. Now, balloons in lab, you're going to in class you're going to do sort of a conceptual lab where you're going to use balloons to represent electron clouds, and the reason we do that is because balloons are a good representation of electron clouds, because they sort of push each other away. They like to have their own space, and so balloons are good models for the electron clouds that surround a central atom. And so the central atom in each of these cases would be represented by the knots that connect the balloons. And so the central atom in these cases would be at the center of these balloons. So we're going to start with electron clouds. We're going to look at these balloons a little bit in lab, and as we do examples here next. Okay, so we're going to start with carbon dioxide. Carbon dioxide has this Lewis dot structure. Carbon is the central atom, so that's the one we're going to focus on. It has 1, 2 attached atoms, and it has 0 lone pairs on the central atom. We're only focusing on the central atom. I know that the 2 oxygens on the outside do have lone pairs, but we're just focused on this carbon in the middle. 2 attached atoms plus 0 lone pairs means we need 2 electron clouds on this central atom. So that means we need 2 balloons. Remember, the electron clouds are represented with balloons, 1 for each electron cloud. And when we connect these to each other, they're going to separate as far apart as possible. The knot, you can imagine that the carbon is at the knot where those 2 balloons connect to each other. And so because they separate as far apart as possible, they're going to separate at a 180-degree angle. And that means they have a linear geometry. We're going to talk about that a little bit later, all the names. Here, boron is the central atom. It has 1, 2, 3 attached atoms. It has 0 lone pairs, which means it has 3 electron clouds, which means we need 3 balloons. So we're going to draw our balloons here. 1, 2, 3. 3 different balloons are going to separate as far apart as possible, and they're going to form 120-degree angles with each other because that's the best separation between the 3 balloons, among the 3 balloons. This geometry is called trigonal planar because it is triangular in shape. That's where the trigonal comes from. It looks like a triangle. And planar means it is flat. And so flat, meaning if I flipped it up on its side and turned it, I would realize that it is not three-dimensional, that it is very, very flat, right? So it's kind of flat in shape. Looks kind of like a Dorito. We could call it Dorito shaped, but that's not what they called it. Probably Doritos hadn't been invented at that time, and so probably that's why they call it trigonal planar, even though Dorito shaped is much more interesting. We'll stick with trigonal planar. Next, we have carbon tetrachloride. If we focus on the central atom, which is carbon, and we count the number of attached atoms, we have 1, 2, 3, 4 attached atoms. We have 0 lone pairs, which means we have 4 electron clouds, which means we need 4 balloons. 4 balloons are going to connect to each other. And rather than just use the 2 dimensions that the previous 2 have used, the 4th balloon is going to force itself out into a 3rd dimension. So I'm going to try to draw these balloons 3-dimensionally. It's not easy to do, but these form what is called a tetrahedral geometry, where the carbon is at the knot in the middle. Now these 2 chlorines, so the way we draw this is solid lines are represented, they're understood to be in the same plane as the paper. And then we do this weird wedge to mean that it is coming out of the paper toward you. So that chlorine with the wedge is coming out of the paper in the direction of you. And then to denote something going back into the paper, we use these dashed lines. So dashed line is going back into the paper. So this geometry is called tetrahedral. And we're going to look more at that in a few minutes. If we move on, ammonia is similar to carbon tetrachloride. The central atom is nitrogen. That central atom has 1, 2, 3 attached atoms. It also has 1 lone pair. This is the first example we've seen with a lone pair. 3 plus 1 means it has 4 electron clouds because that lone pair needs to be somewhere. So it's going to have 4 balloons just like the other one did. So we're going to draw the nitrogen with 1, 2, 3rd balloon we'll draw coming out towards you, and then the 4th balloon is going away from you. So the difference here is that one of those balloons is going to house a lone pair. And so we're going to put a hydrogen here, and we're going to put another hydrogen in the same plane, and we're going to do another hydrogen with the wedge coming out towards you. And then going back into the paper is the lone pair. So the difference here is that lone pairs are invisible. You can't see them. The geometry is not defined using the lone pairs. So before, we had a tetrahedral geometry that you see here. Carbon tetrachloride is tetrahedral, and that is the name of its molecular geometry. But the difference here, and the reason we don't call this one tetrahedral, is because lone pairs are invisible. You can't see the electrons. There's no atom there. So you have to sort of ignore that it's there. I'm going to redraw this just so that it's sort of in a different orientation. And we're going to look at three-dimensional models of this as well that I think will make it clearly a little more clear. But if I draw the same, I just rotated the molecule, right, so that I sort of flipped this hydrogen down. Then now you can see that we have a nitrogen in the center, and then this one hydrogen going to the right and down is in the same plane as the paper or as the screen. Then this one hydrogen that sort of looks like it's here in the middle is coming towards you, and another hydrogen is going back. When you look at it in this orientation, if you use your imagination, it should look like a pyramid where the nitrogen is at the top of the pyramid and the three hydrogens are at the bottom of the pyramid. The pyramid has a triangular base, and so the name of this geometry is called trigonal pyramidal. Trigonal means it's triangular, the sides are triangular, and the base is triangular. And it forms a pyramid, right? Pretend you're in Egypt. It's not flat, it's a pyramid. So it's not trigonal planar, it's trigonal pyramidal. Now if we look at water, water's Lewis dot structure looks like this. Oxygen is the central atom. The central atom has 2 attached atoms, and it has 2 lone pairs on it, which means 2 attached atoms, 2 lone pairs means it needs 4 electron clouds. 4 balloons, if you will, and so that is going to look a lot like the others did if we imagine the balloon lab, and we have our 4 balloons forming the three-dimensional structure that we saw before. 1 balloon coming towards you, 1 balloon going away. Oxygen is in the center, and we'll draw the hydrogens, 1 up and 1 down and to the right, and then with the wedge and the dashed lines we're going to attach the lone pairs there. Now because these lone pairs are invisible, then they don't help. They're invisible, and so they're not a part of the geometric shape, the molecular shape. However, they're still there, and so because they're there, they help define the angles because they repel the other electron clouds. And that's the same idea that the balloons need space, right? They still take up space even though there's electrons there, even though there's no atom attaching it. So in the electrons, they help define the structure. The lone pairs help define the structure, but you can't see them. So it's almost like there's an invisible force there that forces this molecule into what's called a bent geometry. So water is bent. So now these 3 geometries, they all have the same number of electron clouds. The tetrahedral geometry, these angles are all separated by 109.5 degrees. So the chlorine bond angle is 109.5 degrees. So the chlorine bond angle is 109.5 degrees. Now the bond angles for ammonia and water may seem, they're actually very close to 109.5 degrees, but they're not exactly 109.5 degrees. And the reason for that is because the lone pair of electrons actually compresses that bond angle. It actually takes up more space than one that would be sort of reined in by another atom over here. And so the lone pair repels the other clouds, and it's sort of like having a slightly bigger balloon there. Okay, it's like if you blew that one up a little bit more with a little bit more air, then it takes up a little bit more space. And that's only because it doesn't have an atom on the other side to sort of keep it compressed, keep it compact. And so it expands a little bit more. And so that actually compresses the other bond angles to be only about 107 degrees. And then water is compressed even more because it has 2 lone pairs, which are housed in 2 different balloons, 2 different electron clouds, and they're going to compress it even more, so it ends up being about 105 degrees. PCl5 is our next example. These lines are sometimes used instead of dots if you're being really fast. So the central atom, phosphorus, has 1, 2, 3, 4, 5 attached atoms and 0 lone pairs, which means it has 5 electron clouds, which means we have 5 balloons. So when you connect 5 balloons, you end up getting a geometry that looks sort of like this, where you have 3 balloons along sort of the equator. We call those equatorial. And then we have 1 balloon up and 1 balloon down. Those 2 that are shown here in orange are called axial. They are not the same as the equatorial positions. We now all of a sudden have a geometry where the different positions, the different atoms that are attached to phosphorus, are going to occupy slightly different positions around the atom. And the reason they're not all exactly the same is because the equatorial positions separate out into that whole central equator plane, and they end up being 120 degrees apart from each other, whereas the axial positions are 90 degrees away from the equatorial positions. And so they're not all exactly the same. The axial and the equatorial positions are not identical. So here we're going to put the chlorines, attach them in. Remember that the flat lines are in the same plane. The wedge comes out of the paper, and the dashed line goes back into the paper. So you can see that here. This would be a drawing that represents we call this perspective view, that supposed to represent the sort of three-dimensional structure. Now here we have sort of a triangular equatorial plane, and then if we connect all of these, then you end up getting a geometry that looks like 2 pyramids on top of each other. So we have 1 pyramid here with a triangular base, so trigonal. And then there's another pyramid upside down on the bottom. So it sort of looks like 2 pyramids connected. So we call it trigonal bipyramidal. So it's trigonal because it's triangular sides, and then bipyramidal because there are 2 pyramids, one on top of the other. The bond angles here, the equatorial positions are 120 degrees apart from each other. The axial positions are 90 degrees apart from each of the equatorial positions. So that's a 90-degree bond angle there from one equatorial to the axial position. All of these are 90 degrees. So the 3 equatorial positions are 90 degrees from each axial position. But I think what I'm trying to show you next is the equatorial positions are 120 degrees apart from each other. So here, if we sort of rotate this down and look from the top, then now we have this chlorine. We're going to zoom in from there, from the top chlorine, and we're going to look just at the phosphorus. There. Now this is the middle plane. So we've already sort of zoomed past the top chlorine, and we're between chlorine and phosphorus, and now we're just looking at those 3 chlorines in the equatorial positions. And now they're sort of flat on the page. And you can see the other chlorine is way at the bottom there. So these are 120 degrees apart from each other. Now let's look at SF6. This is the Lewis dot structure. Sulfur in the center. Has 6 attached atoms. 1, 2, 3, 4, 5, 6. There are 0 lone pairs, which gives us 6 electron clouds, which means we need 6 balloons. So if we attach 6 balloons to each other, then they're going to separate out as far as possible from each other. And you end up getting a structure that looks sort of like this, where these 2 balloons that I've colored red are coming towards you, then there's 2 balloons behind them going away from you, and then there's a balloon at the top and a balloon at the bottom. And so now all of these balloons are 90 degrees apart from each other, and this gives you what's called an octahedral geometry. If we add in the fluorines, then we have 2 wedges coming towards you, and 2 dashed lines going back into the board or the screen or the paper, and that looks like this. So here, this is called octahedral, and the reason for that is because it forms what's called an octahedron. And so if you connect all of the outer atoms, the fluorines, to each other, then you end up getting an 8-sided figure. So it kind of looks like square bipyramidal. It looks like two square pyramids on top of each other, but since it forms 8 equal triangular sides, we call that an octahedron. These positions are all the same, so this is sort of what an octahedron would look like over here. We have 1, 2, 3, 4, back here in the back, 5, 6, 7 over here on the left, 8 in the very back. That's 8-sided figure. So that's an octahedron. All the bond angles are 90 degrees. So all the positions are equivalent now. Now we're going to add some lone pairs to some structures just to see what that effect is. Now we have SF4 and ClF3 as examples. SF4's Lewis dot structure has sulfur as the central atom. We have 4 attached fluorines and we have 1 lone pair. So that gives us 4 plus 1, which is 5 electron clouds, which means we need 5 balloons. So it's going to be kind of like PCl5, except one of the balloons is going to house a lone pair. So now we have this 5, we have the 3 equatorial positions, and we have the 2 axial positions. So this is my balloons, right? And the sulfur in the center is where all of them come together. Now remember, the lone pairs are invisible, and so one of these balloons is going to house the lone pair. But because these positions are not identical, we have to be careful about which one we choose. So the lone pairs, the lone pair could go in an equatorial balloon, or it could go in an axial balloon. And we have to figure out which one is better for it. So electrons, so this just says positions are not equivalent. Electrons like space, right? They like to spread out. Remember, the electrons in NH3 and H2O tended to spread out a lot. So because electrons like their space, they're going to be sitting housed in an equatorial spot rather than an axial spot, because the equatorial spot here is 120 degrees away from 2 atoms and then 90 degrees away from 2 others. But in the axial position, it's 90 degrees away from 3 atoms, and so it gives it more space if we put it in an equatorial spot. So the lone pair occupies the equatorial position in preference to the axial position because it can spread out more space. So it ends up looking like this. We call this a seesaw geometry. And it's not totally obvious why that is, but if we flip it down on its side, where these 2 straight ones are going left to right, and then the 2 120 degree apart equatorial positions are sort of sitting on the ground like the 2 legs of a seesaw, then you can imagine if there's some little kids on there that they can seesaw back and forth. Now let's look at ClF3. So ClF3, chlorine trifluoride, has 1, 2, 3 attached atoms attached to the lone pair, to the central atom. It has 2 lone pairs, which means it has 3 plus 2, 5 electron clouds, 5 balloons. Just like the previous 2, PCl5 and SF4 that we looked at. Now if you remember, so it's just like this one. But we have a second lone pair now, right? So it's just like this. The second lone pair is going to occupy the another equatorial position. So you end up with this shape, where, remember, the lone pairs are invisible. All you see are the atoms. And so if you look at this shape, it looks kind of like a T, so we call this T-shaped. The bond angles are 90 degrees, and there's an angle here that's 180 degrees. We got, I think, one more to look at. This is antimony pentachloride. That's an interesting molecule. SbCl5 minus 2. It's an ion. So Sb in the center has 1, 2, 3, 4, 5 attached atoms and 1 lone pair. Means it has 6 electron clouds or 6 balloons. So this will form the octahedral geometry that we looked at before with the balloons at least, but there is a lone pair. So in this case, the lone pair occupies, all the positions are equal, so you can pick any spot for the lone pair to occupy because all positions are equal. You end up with this geometry, which if I draw it a slightly different way, I'm just going to rotate it, then we end up with, we put the lone pair at the bottom instead of over here in the front right. I put the lone pair on the very bottom. And so now it's just a little bit more obvious what the structure is. We can connect the sides into a pyramid with a square base. And so so this is a square pyramidal geometry rather than a trigonal pyramidal geometry. It's a pyramid with a square base. Square pyramidal. So now that's because of the base, and it's pyramidal because it's pyramid. XeF4 xenon tetrafluoride has 4 attached fluorines and 2 lone pairs on the central xenon atom, which means it needs 6 electron clouds, 6 balloons. So it's again going to be octahedral in its balloon geometry, just like before. Now we need to find another position for the lone pair. Now, in this case, since one lone pair is going to occupy one position, the other lone pair is going to choose to be as far away as possible, and so it's going to be 180 degrees away from it. So that way they get to spread out as much as possible. So now I'm going to draw it this way, where I put the lone pairs sort of in the one coming towards you to the right and the one going back into the left. But if I redraw this, this is more obvious when you have three-dimensional models, but I'm going to redraw this just to rotate it a little bit. So now you can see all of these fluorines are flat on the page and all of the angles are 90 degrees. So this is called a square planar geometry. There's 180 degrees from one fluorine to the next, and then 90 degrees from some fluorines to another fluorine. So this is called a square planar geometry because it forms a square square like this. I'm connecting the fluorines, and it's planar, so it's flat. So there are a few other geometries, but these are the main ones that we're going to look at. So we can see that balloons are a good way of modeling the electron clouds because they take up space. And the electron clouds are going to separate the same way balloons do and give themselves as much space as possible and divide out, separate into 3 dimensions as well as they can. So the number of electron clouds or balloons would determine the electron cloud geometry, right? So 2 clouds or 2 balloons would be linear, 3 clouds would be trigonal planar with 120 degree bond angles, 4 clouds would be tetrahedral, 5 clouds would be trigonal bipyramidal, and 6 clouds would be octahedral. So the electron cloud geometry is not usually what we care about. Usually what we talk about is the molecular geometry, where knowing that the electrons, the lone pairs of electrons are invisible, you would only care where the atoms are. And so we're going to look at these more carefully and sort of talk more about the molecular geometry next. But first I wanted to you these are the 5 different possible electron cloud geometries. This is just a different representation. These are the corresponding bond angles. So a linear geometry would be 180 degrees, trigonal planar would be 120, tetrahedral would be 109.5 degrees. Trigonal bipyramidal has the 2 different positions, equatorial positions, which are 120 degrees away from each other, and then the axial positions, which are 90 degrees away from the equatorial positions. And then the octahedral geometry would have 6 electron clouds, and they would all be 90 degrees apart. Look at each one. When there are 2 clouds, then you end up getting a linear electron cloud geometry and a linear molecular geometry as well. What this would be when you have a central atom with 2 attached atoms and 0 lone pairs. Carbon dioxide is the example we used earlier, but HCN is another example that you see shown here. If we move on, when there are 3 clouds present, then you have a trigonal planar electron cloud geometry, and then you might have a trigonal planar molecular geometry, or if there's a lone pair present in one of these clouds, then you would have a bent geometry. For example, what you see here, the top is a formaldehyde molecule, CH2O, where you see that it divides up into a trigonal planar molecular geometry with approximately 120 degree bond angles. The hydrogens are a little closer to each other simply because they're smaller, but 120 degrees would be fine for bond angles for that. But the bottom is what I wanted you to pay closer attention to, because we haven't seen this type of molecule yet, where you have a central atom with two attached atoms and one lone pair. It divides up with a 120-degree bond angle, but we call this geometry bent because that lone pair is invisible, right? So a good example of this would be SO2, like you see here. 4 electron clouds is going to give you a tetrahedral electron cloud geometry. I looked at these 3 examples, but remember that a tetrahedron, a regular tetrahedron is shown on the left. It's a 4-sided figure, and the carbon would be where the central dot is shown there. Geometries you get with a tetrahedral electron cloud geometry, we've already discussed these a little bit. Methane CH4 is like the carbon tetrachloride example we had earlier, where the molecular geometry is called tetrahedral. The one in the middle is a trigonal pyramidal molecular geometry, and the example we gave earlier, and the one here as well, is ammonia, where the central nitrogen has 3 attached hydrogens and then 1 lone pair, and the lone pair is invisible so you can't see it, but it still occupies space, so it pushes the other ones down so that they're about 107 degrees apart from each other. And then at the bottom is a water molecule, which has what's called a bent molecular geometry, and the bond angle is about 104.5 degrees. I think earlier I told you 105 degrees. Either one of those is fine. And that's simply because those lone pairs, they take up space. They actually take up more space as lone pairs than they do as a shared covalent bond. And so they compress that bond a little bit more than they normally would. So the lone pairs spread out a lot, and that compresses the bond angle a little bit. So we've already looked at these a little. When you have 5 electron clouds, you end up with a trigonal bipyramidal electron cloud geometry, and we've already looked at this, and we've already looked at the molecular geometries that come from here. But this image might help more than my drawing, where you see a trigonal bipyramidal geometry. On the left is 2 triangular pyramids, and they're there are 2 of them connected, and that's why it's called a bipyramid. And you see the equatorial and axial positions shown very clearly. The equatorial positions are shown in blue, and the axial positions are shown in red. And then there's a top view where you can see that the equatorial positions are 120 degrees apart from each other. The different molecular geometries we've already looked at. PCl5 has a trigonal bipyramidal molecular geometry. SF4 has a seesaw molecular geometry, and you can kind of see that's because it has 1 lone pair occupying an equatorial position. ClF3 is T-shaped, and we already looked at that one as well. There's a 4th one on here that I forgot to show you, and that is a triiodide molecule, and that's in the upper right-hand corner here. So triiodide has 2 attached atoms and 3 lone pairs on the central atom. And so all 3 lone pairs are going to occupy the equatorial positions because they can spread out the most in that spot. And that's going to give you a linear geometry here. So you can see that sometimes you get the same name geometry even from different numbers of attached atoms and lone pairs, right? So for example, we've seen 2 different bent geometries, and we've seen 2 different linear geometries with different electron cloud geometries. So it helps to just go through the steps. You look at the central atom, you count the number of attached atoms, you add in the number of lone pairs. That gives you the number of balloons or electron clouds, which tells you the electron cloud geometry. And then you place the lone pairs in the appropriate places, the appropriate balloons. If they're equal, it doesn't matter where you put them. If they're not equal, you have to decide. In this case, they would go in an equatorial position because they can spread out more. So just remember, they like to spread out. And then you ignore the lone pairs because they're invisible to your eyeballs, and then you just look at the atoms to decide what geometry it is. Finally, octahedral electron geometry. This on the left is a regular octahedron with 8 sides. And you can see here all the positions are equal now. That's why they're all colored the same color. They're all 90 degrees apart. And here we have 3 different examples. SF6 is octahedral. We already looked at this example. SbCl5 minus 2, I believe that's antimony pentachloride ion. That's weird. It has a square pyramidal shape. We already went over that one. And then XeF4 xenon tetrafluoride, the second lone pair is going to occupy the the electron cloud on the opposite side of the molecule just to spread out more, and you end up getting a square planar shape. This table just synopsizes everything, so it might help if you sort of use this when you study and try to commit some of these names to memory. So you would just need to look at how many attached atoms there are, the number of lone pairs, you add those up, and that gives you the number of charge clouds. The number of charge clouds is going to determine the electron cloud geometry, and then once you know that, you would then look at how many lone pairs are on the central atom, and that helps you deduce the molecular geometry or shape. There's some examples, and then this is the end of the table where you end up with 5 and 6 electron clouds.